Hello, everyone. I'm Zixuan. I'm a third-year grad student at UCSB working with Crystal Martin. Today is my honor to present my recently submitted work on the physical region of Outflowing cloud in local star-forming galaxies. So our research is based on the Galaxies survey. Galaxies contains of 45 local UV bright galaxies that spans a wide range of physical properties that are similar to the high redshift galaxies during the epoch organizations. Last year, we observed 14 classic galaxies using the KITP spectrograph and imager with a 1.25 times 20 arcsecond slit. In the left panel here, I show how do we constrain the kinematics of these galaxies using multiple component model. Here, I'm showing how we fit the O3 5/7 lines. And the right panel here, we show how do we place the ESI slit on the brightest node of each galaxy. And in summary, we actually find that 13 out of 14 galaxies of our samples actually need the triple component model to fit the strong lines like H alpha and O3 5/7s. And in comparison to most of the outflow studies in the literature, we actually find there are two outflowing components, the broad and very broad, and they are distinct with each other in terms of their velocity width and also their flux fraction to the total flux. For example, the typical velocity width of the broad components is around 250 kilometers per second, but for the very broad, it's surprisingly high as 1,000 kilometers per second. So this result made us wonder what are the physical regions of these outflowing components and whether they chase the same gas. To shed light on that, we can plot their scaling relations with galaxy observables. For example, we can plot their maximum velocity versus the star formation rate of each galaxy. Here, the blue and the pink dashed lines here show the best fitting linear relations for the very broad and broad components, and the orange dashed line here shows the best fitting relation based on the UV absorption lines, both based on the whole Galaxy sample. As you can see very clearly that the broad components have very different scaling relations as the very broad components, which might suggest they chase different gas. And they have a similar scaling relation as the UV absorption lines within two standard deviations. And to physically interpret their physical regions, we found that the scatter of the broad components can be explained by energy-driven and momentum-driven superbubble models with different bubble expansion times and ISM ambient densities. In contrast, for the very broad components, we found that their scatters can be explained by different galactic wing models with different mass loading factors of the Hall phase. So our conclusion here is that we basically suggest the broad component is actually chasing the expanding superbubble shells, but the very broad components here are actually the one that is chasing the free-floating galactic wing that are formed from the superbubble blowout. And another, there's another paper we accepted earlier this year. We reached a similar conclusion based on one of these galaxies, using IFU data. And another interesting fact we found for our study is that what we call the luminosity deficit issue of the galactic wing model. Here we compare our observations to the state-of-the-art multi-phase galactic wing model by Fieldy and Brown in 2022. In both of our panels here, the x-axis is the velocity width and the y-axis is the O3 5/7 luminosity. And the observed broad and very broad component are shown as the open and field markers. The polygon shapes represent the model predictions, and both observations and the model predictions are color-coded by their star formation rate surface densities. So as you can see very clearly that galactic wing models can better reproduce the velocity width of the very broad components in comparison to the broad component, because we suggest that broad component is actually tracing the expanding superbubble shells. But we also found that they underestimate the observed O3 5/7 luminosity by 1 to 3 orders of magnitude. Which means that, in other words, the galactic wing model only considers the supernova feedback. The mechanical energy from the supernova feedback cannot explain the observed O3 of luminosities. And we argue that most of the luminosity are actually coming from stellar photonization based on the BBT diagram. So our main takeaway points here is that we should be aware of these kind of very extreme outflows in local star-forming galaxies with a full heat max larger than 1,000 kilometers per second, and they are observed in both forbidden and permitted lines. And these points are connected to the high redshift galaxy and AGN studies because we know that the full heat max of 1,000 kilometers per second is always like set as a threshold to distinguish outflows powered by an AGN and star-forming galaxies, because we know like most of star-forming galaxies has a Fulvis max less than, for example, 400 or 500 kilometers per second. But based on our studies, we know that this is probably not just galactic ring, but explaining superbus shells. Yeah, I think that's all for my presentation, and really happy to talk about more later. Yeah, thank you.